देवासर स्क्रीन नजर आ रही है?
हेलो।
देवासर,
हाँ सर।
इज इट विजिबल?
हाँ सर, स्क्रीन तो आ रहा है मुझे।
ओके। So we'll start at 12 o'clock. So should we start, sir? Phanisankar, sir, should we start?
Yes, I am ready.
Okay. So let me introduce our today's guest expert, Mr. Phanisankar Chilukuri. He is the Chief Manager at Grid Controller of India, Grid India, New Delhi, and a senior member of IEEE and member of SIGRE. He holds an MTech in Power Systems from IIT Delhi and has been with Grid India National Load Dispatch Center since 2013. He made significant contributions to the implementation of automatic generation control, security constrained economic dispatch, and security constrained unit commitment, tertiary, reserve, ancillary services in Indian power system. He is the recipient of Power Grid IEEE India Council Young Engineer Award 2021 and the NPSC Young Engineer Award Industry 2024. So in today's presentation, I welcome him and I request him to start his presentation.
Right. So you all can see my screen. Can you confirm, sir?
Sure, sir, sure. It's visible.
Yes, yes. Thank you for that kind introduction. So the topic for this session is on automatic generation control. Automatic generation control, particularly its implementation in the Indian power system. So that's what I'll cover now. Okay. So this is the outline that I'll cover. Just let me increase my. So you're able to hear me loud and clear, right?
Yes, sir. Yes, sir.
Right. So, so these are the four pillars of market design, the basic pillars of market design. So you might have. So
I
these are the
request
four basic pillars of market design.
participants to mute their
Scheduling.
speakers. I request participants to mute their speakers.
So these are the four pillars of market design: scheduling and dispatch. Let me just. Scheduling and dispatch, congestion management, ancillary services, and imbalance and deviations. So in any power system, these four basic pillars hold good. And in Indian power system also, all these four pillars are already present. So the topic of automatic generation control, it falls in this third pillar, which is ancillary services. Okay. So scheduling and dispatch is based on the previous uh, looking at a day-ahead basis and based on the forecast of the particular area, and based on that, some resources are allocated to maintain load generation balance in the system. And if there is any congestion between two areas, then congestion management is done so that, and if needed, rescheduling and redispatch are also done to alleviate this congestion. Even after having a perfect scheduling and dispatch and having a very good congestion management, still in the real time, there is always some scope for uncertainty, because uncertainty is a way of life in power systems. So every day, something or the other will happen. Like someday it will rain, someday there will be high temperature, someday it will be very cold, someday there will be a festival. Like that, there will be so many uncertainties. Even though we have planned for some of those known factors, there will still be some deviation from the forecast. So that deviation from forecast is handled through the third pillar, which is ancillary services. And even after having a good scheduling and dispatch, doing congestion management, and having ancillary service also, there will be some imbalance and deviation in the real time. Like if you ask a power plant to generate 400 megawatt, it will generate 398 megawatt. Sometimes it will generate 402 megawatt. So um, that will be handled in imbalance and deviation. Similarly, if you ask a draw entity also to exactly draw a particular megawatt, it may not do so. So that is handled in deviation. So all these four pillars are handled by means of the grid code and by means of CRC regulations. And we have Indian electricity grid code. There are measures to relieve congestion in the real time for congestion management. There is a ancillary services regulation for ancillary services, and there is a deviation settlement mechanism for imbalance and deviations. Okay, and today we will discuss more about this ancillary services, particularly on the secondary reserve ancillary services, which is implemented through AGC. While we take up all these aspects, the basic objectives of the grid code, they still remain, like frequency control, voltage control, managing tie line flows, managing the system stability, managing the international flows, ensuring reliability in the system. Whatever actions we take, they should be both economical and sustainable also. When I say economical, whatever actions we take under ancillary service also, they should be based on merit order dispatch. Similarly, sustainability means we should not, use up all the uh, unsustainable resources. Like if we run, let's say, if we have, let's say, a lot of battery storage in India, then obviously we will have better management. But there is a cost to it, like so. The sustainability aspect also should be seen while we deploy the resources. So this is the ancillary services classification that is given in the Indian Electricity Grid Code. We have broadly ancillary services are demarcated into three types: frequency control, voltage control, and black start. And the frequency control ancillary services are demarcated into primary, secondary, and tertiary frequency control mechanisms. So the topic for today is automatic generation control, which is secondary frequency control, which is operationalized through AGC and which is regulated through SRAS, Secondary Reserve Ancillary Services Mechanism. Tertiary frequency control, the reserves are procured through market-based. It is also regulated through the Tertiary Reserve Ancillary Services Mechanism. There are other ancillary services like voltage control and black start, where provisions are provided in the regulated mode in IGC 2023. So the topic for today is secondary frequency control, which is regulated through SRAS and which is operationalized through automatic generation control or AGC. Okay. So like we discussed, after any disturbance, let's say the frequency before the disturbance is 50 hertz. If there is a sudden generation tripping in the grid, then the frequency will immediately fall. So the immediate rate of change of frequency is arrested by the system inertia. Then after a few seconds, after the frequency crosses the dead band, primary frequency control will immediately kick in. It will try to restore the frequency back to the quasi steady state frequency. And this primary frequency control and inertia, they have to be replenished. So the secondary frequency control, it will try to replenish the primary frequency control, and it will try to bring back the frequency to the nominal frequency or the 50 hertz. Similarly, tertiary frequency control will be dispatched so that it will replenish both secondary and primary frequency control so that we are able to handle any next contingency. Okay. So because like I told, uncertainty is a way of life in power systems. Just because a contingency is happening now, there is no guarantee that a contingency will not happen 5 minutes later. So we have to be always ready. We have to be always N-1 compliant. So that's why we need a frequency control continuum to manage the frequency, to replenish the primary reserves, and so that we are very close to the nominal frequency always, and we are ready to handle any next contingencies like that. So the primary frequency reserves, they start the start of activation is immediately as soon as the frequency crosses the dead band, and the dead band is presently plus or minus 0.03 hertz from 50 hertz, and the full availability is expected within 45 seconds. And the expected ability to sustain the full deployment of primary response is up to 5 minutes. Secondary frequency control will start activating within 30 seconds after the receipt of the AGC signal, and the full availability or deployment factoring the ramp rate is within 15 minutes. So the secondary frequency control should be fully deployed within 15 minutes, and the ability to sustain is up to 30 minutes or till replaced by the tertiary reserves. Similarly, tertiary reserves will be dispatched block by block, and they have to start activation within 15 minutes of dispatch instructions from the National Dispatch Center, factoring ramp rate, and the ability to sustain the full deployment is up to 60 minutes. So secondary reserve ancillary services, primary reserve ancillary services are actually deployed through the governor response. Secondary reserve ancillary services are dispatched through automatic generation control or AGC, and tertiary reserve ancillary services are dispatched through IT-based mechanism from the National Dispatch Center. So the main topic for today is secondary reserve ancillary services, which are dispatched through automatic generation control, and the start of activation is within 30 seconds, the desired start of activation, and the full availability or deployment is expected within 15 minutes, and the ability to sustain full deployment is 30 minutes or till replaced by the tertiary reserves. Okay. So these are the regulations and procedures. I'll share this PPT uh, with Sanjeev sir, and see, you can I have provided links here. You can click and read. So AGC is guided by Central Electricity Regulatory Commission Ancillary Services Regulations 2022. So there is a detailed statement of reasons and why this what is this regulation say, and there are some implementation aspects are also covered in the CRC orders. And based on these regulations, there is a detailed procedure of second reserve ancillary services or AGC, which is available on National Dispatch Center website. I have provided the link here. And the Indian Electricity Grid Code also refers to the second reserve ancillary service regulations, which you know which uh, fortifies the second reserve ancillary services regulations 2022, and which empowers these detailed procedure to be enforced. And there is a procedure for performance assessment and procurement of resource also. So I've provided links here. You can just click and read uh, those who are interested. So what is automatic generation control? Automatic generation control is a 24/7 mechanism. It is an automatic and supplementary control mechanism. Uh, the purpose of automatic generation control is to control the frequency and tie line flows. So there are several signals that are exchanged between the National Dispatch Center AGC software and the power plant through long distance fiber optic cables every 4 seconds. AGC helps replenish the exhausted primary reserves so that we are ready to handle any next contingency. And this is an efficient and automatic frequency control mechanism during high RE periods. And AGC improves the reliability of the Indian power system. So we will discuss more about this. So in AGC, every 4 seconds, signals are exchanged between NLCG software and the power plant through long distance fiber optic cables. So this is the AGC project status as on date. There are 83 power plants with around 80 gigawatt capacity that is under AGC. Around 213 units are wired under AGC as on date. Out of this, 70 gigawatt is coal-based, 6.6 gigawatt is hydro, 3 gigawatt is gas-based. We also have conducted pilot projects on 180 megawatt solar power plant, 20 megawatt, 40 megawatt or battery energy storage system, and a 2 into 250 megawatt pumped hydro project also. We have conducted AGC pilot projects. So, and these 83 power plants are operational 24/7. Okay, around plus or minus 5% of reserves is provided from each generator for the second reserve ancillary services, and up and down regulation of around 1500 to 2000 megawatt we receive from all these plants, because some of these plants are fully scheduled. Some of these plants, they are scheduled up to the minimum turn down level or the technical minimum, so they cannot provide down regulation. Those plants which are fully scheduled, they cannot provide up regulation, like that. And all these power plants combined, they provide around 200 to 250 megawatt per minute ramp rate. Suppose if you consider a normal thermal power plant, it will provide 5 megawatt per minute or 10 megawatt per minute ramp rate. But this is the power of unity. Like, we have so many power plants under AGC, so the combined ramp rate that these power plants provide is up to 200 to 250 megawatt per minute. And uh, there are there are some power plants like Loktak, which is around 2,500 kilometers away from Delhi, in the northeastern region. Like there is a NTPL Tuticorin, which is also more than 2,500 kilometers away from Delhi, and they're also controlled under AGC every day. Okay, so the one important concept while we learn about AGC is the area control error. So how to calculate the area control error? So there is a detailed procedure in our detailed procedure website, in the website, in the detailed procedure, how to calculate ACE and what are the parameters that have to be taken for calculating ACE. So the for calculating ACE, each region is considered as a balancing area. Like northern region is one balancing area, west, east, northeast, and south. These are the different balancing areas for calculation of ACE. So the formula for ACE is IA minus IS minus 10 into BF into FA minus FS plus offset. So IA is the actual net interchange in megawatt. The sign convention used is positive for export. It's the same sign convention as in Indian Electricity Grid Code, and in several other countries also use the same sign convention. And IS is the scheduled net interchange in megawatt. So if the actual net interchange is equal to the scheduled net interchange, then this first term will be zero, right? IA minus IS will be zero. Similarly, FS is the scheduled system frequency, which is 50 hertz for Indian power system, and FA is the actual system frequency. So if FA is equal to FS, then the second term will be zero. The purpose of AGC is to drive this area control error towards zero. That means to drive this IA towards IS and the actual frequency towards 50 hertz. Offset is for provision for compensating errors such as measurement error. Usually the default value is zero. So the sign convention is like this, that AS is positive, that means the area is in surplus and its internal generation has to back down. Similarly, the AS is negative, means the area is in deficit and its internal generation has to increase. So that is the sign convention. For BF, this is the frequency bias coefficient. For this, we take the frequency response characteristic. We calculate the frequency response characteristic of each region for a continuous of more than 1,000 megawatt and above. So we take the median value of the previous 20 events, the frequency response characteristic of the previous 20 events, and we use that as a proxy for frequency bias coefficient. Just a minute, please. हाँ हेलो. हाँ सर बताइए. हाँ. राइट राइट. करेक्ट सर. राइट. ओके. राइट राइट. करेक्ट सर. राइट राइट. राइट सर. यस सर. राइट सर. राइट राइट. सर राइट. ओके सर. ओके. तो उसको इंक्लूड कर देंगे सर, पूरा फॉर्म को इंक्लूड कर देंगे. राइट राइट. ओके. राइट राइट. मेल कर देंगे सर, इंक्लूड कर देंगे. यस सर. ये जस्ट मैं एक क्लास में हूँ, मैं आपसे बात करता हूँ सर. Sorry for that. Right. Uh, uh, so we are there here, right? So uh, the purpose of AGC is to drive this area controller towards zero, and uh, for frequency bias coefficient, like I have told, we took some reference from this IEEE Task Force report of 2017, and we calculate the frequency response characteristic of each region by looking at how the region responds when there is a contingency, actual contingency in that region, like when there is generation tripping or a load loss in that particular region. We observe the behavior of that region, we record that, and we calculate the megawatt per hertz response of that region for a deviation of, let's say, 1000 megawatt and above, how much megawatt is that area responding? So that we calculate and we take the median value of that those responses, and we use that as a proxy for frequency based coefficient. Okay. So like that we calculate ACE, and the purpose of AGC is to drive this area control error towards zero. So in AGC, what we do is we have a typical thermal power plant. This is a typical thermal power plant load control scheme. So the AGC correction is fed at uh, the load set point. So in AGC, we change the load set point. The signal is not directly given to the governor, whereas like in primary response, the signal is directly given to the governor. In AGC, the signal is sent to the load set point. Because we are sending the signal to the load set point, so the more coal will be burnt if we need up regulation, and less coal will be burnt if we need down regulation. So the in any typical power plant load control scheme, there are three modes of operation like turbine follow, boiler follow, and a coordinated mode. So turbine follow means first the boiler will respond um, by increasing its temperature and pressure parameters of the boiler. First, the boiler will respond and the turbine will follow. The turbine valves will be opened later on. In boiler follow mode, first the boiler will first the turbine will respond by just opening the walls of the turbine governor, and the boiler will follow by maintaining the steam parameters. Coordinated mode means both the turbine follow and boiler follow mode are coordinated seamlessly. The CMC or the coordinated master control mode, it matches the turbine load changes non-linearly with the actual boiler response, and we try to get a smooth output. So the main point here is this CMC also has some controllers. So those all have to be tuned properly for getting a smooth response under AGC. Okay. And we change the load set point in AGC. So those are the two main points that you have to remember. So there are multiple stakeholders involved in the AGC implementation, like NLDC and RLDCs are the nodal agency. So we have the AGC software here at the National Dispatch Center. We are responsible for the system operation and for creation of schedules and for the frequency control. We have industry grade software for which we do the acceptances and customization if needed. SRS providers are the AGC power plants, which actually procure the hardware for interconnecting their equipment, their digital control system with NLDC. They exchange signals with NLDC, and they do the closed loop testing and open loop testing, and they submit the weekly uh, accounts for the energy data submission. The communication is provided by the central transmission utility. They provide the wideband communication, and regional power committees are responsible for accounts performance settlement. And the central electricity regulator provides the regulations for ancillary services, and there are performance-based incentives for the power plants which are participating under IGC. And these regulations also evolve because these are not fixed, because of the disruptive technologies like RE and storage and IBRs which we are seeing. These regulations are also gradually evolving. So, so in AGC, what are the key components? The key components are the coordinate master control, which we talked about, which is at the power plant. So this power plant digital control system is hardwired with a dedicated remote terminal unit, which is housed inside the premises of the power plant. So this RTU is a dedicated RTU for the AGC. Okay. And this RTU is through Ethernet cables. It is connected to a router cum firewall, and suitable uh, uh, media converters are placed from light to Ethernet, so on. Conversions are needed sometimes. And through fiber optic cable, this communication will reach the nearest wideband node. From there, through IEC 104 protocol, through long distance fiber optic cables, on the top of the towers, top of this transmission towers, through router cum firewall, these signals reach the NLDC AGC server. We also take tie line flows and frequency for calculation of phase, and uh, we have a dedicated signal list. I'll explain the signal list also in the next slide. And based on that, we provide the AGC set point to the power plant. So the main signal that we send is the AGC set point that is directly sent to the through RTU, through this router and firewall, through the to the power plant. Okay. So this is the AGC integration process flow chart. Like first we establish communication, then the power plant procures an AGC specific RTU if needed, and the plant provides the signals as per the signal is to the through from the digital control system, and the signal address are provided by an LDC. Then point-to-point validation of signals and open loop testing is done by an LDC. And in open loop testing, we send the set point, but the plant only monitors that set point, and it will get a feel of how it will operate under AGC. And we also prepare some dummy accounts, and then the plant is placed under closed loop testing, where the plant actually responds to the AGC signals, and if needed, the control systems are retuned, okay, so that we get the optimal performance under AGC. So this is the AGC signal list. There are so many signals that are exchanged between the power plant and the analysis AGC software. So the main signals are the unit load set point, because in AGC we change the unit load set point, right? So that's why we take the base point or the load set point from the power plant based on the schedule that it has received from the RLDCs or from the states. We also take the actual generation at gross level. All these signals are at gross level before auxiliary consumption. We also get the information of what are the forbidden zones at these power plants, if there are any. We take the maximum and minimum unit capabilities of the power plants in megawatt. We also take how much the power plant is generating under primary response, how it is distributing its set point amongst various units. We also take some feedback signals, like what is the signal that the power plant has sent to the each of its units. We also take some voltage related information, so that we understand at what point on the generator capability curve this power plant is operating. For gas plants, we take exhaust temperature and all. And some digital signals also we take, like circuit breaker status, governor on or off status. There is the power plant is actually free to take the units either in local or remote. If the power plant is in local, that means the power plant can see the AGC signal, but it need not respond. If the power plant is in remote, that means the power plant will respond to the AGC signals. Similarly, the main signal that is sent from an LDC to the power plant is the plant AGC set point. We also send some other signals like SCD output, and if needed, we the NLDC suspends the AGC for that power plant also if there is any communication issue or any reboot that is needed to the NLDC level. So the different signal types are as per the IEC 104 protocol. Like we use single point digital status, double point digital status. Double point digital status means 00011012 11. So 0, 1, 2, and 3 are the double point digital signals, like, and double point digital commands, input analog point, and set point from nodal agency. These are pretty standard signals for IEC 104 protocol. And this is the AGC communication architecture that we use. There are two front-end processor servers at an LDC. Through router and firewall, these signals reach the nearest multiplexer. From this multiplexer, through the IEC 104 protocol, through the long distance fiber optic cables, it reaches the nearest power plant multiplexer. From there, through a router and firewall, it reaches the nearest remote terminal unit. And we try to ensure dual communication and redundancy wherever possible. Okay. Sometimes it is not possible to ensure dual communication and redundancy, but 90% of the cases there will be dual communication and signal redundancy here. The communication providers are those who provide end-to-end redundant communication system between the AGC power plant and an LDC, and it is in accordance with the communication regulations. And in case of intrastate providers, state transmission utility is also involved. There will be network management system which does 24/7 monitoring and maintenance of this communication. And like we discussed, IEC 104 protocol is used. So there are three main services that are provided by AGC. The first service is generation change in response to outages. The second service is the load following during RE integration, and morning peak during morning peak and evening peak. And the third service is the minute-to-minute AGC regulation. So we will see all these three services now. So AGC response during contingencies, like you can see the blue line is the frequency. There was a sudden dip in frequency because of some disturbance. So AGC increased 800 megawatt around in 8 minutes. So at the rate of 100 megawatt per minute, generation was increased so that frequency is restored back to 50 hertz. Similarly, after a load loss of 1500 megawatt load loss in the system, frequency just shot up to 50.1. Then AGC decreased at 300 megawatt within 3 minutes. So during contingencies like generation loss or load loss, AGC quickly reacts by changing the load set points of the generators, which are under remote, and it helps in driving the area controller towards zero and bringing back the frequency towards 50 hertz. Uh, so this is the first service that AGC provides. So second service that AGC provides is, so you can see the orange line here is the frequency, which is continuously above 50 hertz between 7 a.m. to 10 a.m. AGC, what it does is it decreases the conventional power plants by around 1500 megawatt. It has decreased, and from 7 a.m. to 10 a.m. it has continuously issued down regulation to all these power plants with 1500 megawatt. If AGC would not have decreased this conventional power plant, the frequency would have just increased up to 50.1 or 50.2. So, and by doing so, it also allowed high RE penetration also during this solar pickup periods. So here AGC has provided down regulation of around 1500 megawatt, and here down reserve is also fully utilized. So green curve is the down reserve. So the down reserve is fully utilized here. So AGC helps in controlling high frequency period during such solar pickup periods, and it also helps the thermal power plants to save coal and allows high solar integration into the grid. So with more and more RE penetration, manual frequency control is no longer very easy to do like earlier. So now it is AGC that is going to be very important with all this high RE penetration. Okay. The third service that AGC provides is the minute-to-minute regulation, where the sky blue line is the AGC delta P, where it moves uh, above or below 0 megawatt every 4.5 seconds or 5 seconds. So the typical beat period of grid frequency is around 4.5 minutes, where every 4.5 minutes the Indian grid frequency either goes above 50 hertz or below 50 hertz. If you see the general pattern. So AGC also just tries to counter this frequency change, and when the frequency increases, AGC will decrease generation, and the frequency, if it decreases, AGC will increase generation. So on it will continuously do cycling. So it's a 24/7 automatic control, and while enabling this continuous and automatic cycling operation during daily load changes, it also respects the power plant constraints like maximum, minimum, and ramp rate, because the physical constraints of the power plants, they have to be respected. So this is the case with and without AGC. If AGC is under outage, you can see the black line, which is the frequency without AGC, and the red line is the frequency with AGC. So the frequency with AGC is much more well behaved than frequency on the day without AGC. Similarly, you can clearly identify what is the day with AGC and without AGC. The red line day is the day with AGC, and black line day is the day without AGC, and AGC has been revived at this point of time on this on 2nd July, and then AGC started the frequency started behaving well. So there is increased dependence on AGC. That's what I wanted to make from this slide. So like we discussed, without AGC, the frequency would have remained only 14% of the time within the IEGC band of 49.9 to 50.05 hertz. With AGC and TRA support with ancillary services, the frequency remained 90% within the band on this particular day. Similarly, there are so many instances where AGC plays a very key role in bringing the frequency back to the band, particularly on days when there are high forecast errors. The AGC becomes very important. So the typical power plant response under AGC is like the black line is the AGC set point, and the red line is the actual megawatt. you can see that the actual megawatt is following the AGC set point very closely. And while issuing the AGC set point, ramp rate is honored, and we ensure a smooth control of generation. Okay. Like we discussed, the ramp rate of the power plant is honored. You can see all the AGC set points that are given are within this ramp rate limits that are provided by the power plant, where around 4.2 megawatt per minute is the ramp rate that is set by the power plant. So that ramp rate is honored. One important concept that you have to understand is the difference between spinning reserves and ramp constraint reserves. Let us say we have a power plant of 500 megawatt and the power plant is operating at 400 megawatts. So the difference is 100 megawatt, right? So that is called as spinning reserve. So that 100 megawatt, 500 minus 400 is called as spinning reserve. But if the power plant has 1% per minute ramp rate, that means the 500 megawatt unit has 1% per minute ramp rate. That means the ramp rate of the power plant is 5 megawatt per minute. So in the next 15 minutes, that power plant can change only 5 into 15. That means 75 megawatt only it can change in the next 15 minutes. So it can increase its generation by only 75 megawatt, although 100 megawatt is the spinning reserve. So that the 100 megawatt is called as spinning reserve. And because of RAM constraint, we can harness only 75 megawatt in the next 15 minutes. That is called as RAM constraint reserve. Okay. So that is the main difference. So RAM constraint reserve is obviously always lesser than spinning reserve. So the hydro operation under AGC. So hydro plants, several hydro power plants in India, they have Francis turbines. Francis turbines have forbidden zones. They are also called as cavitation zones or high vibratory zones. And these forbidden zone limits are fed into the AGC software through telemetry. And what AGC software does is it prevents sustained operation. It is prohibited in the forbidden zone. So only quick transition is facilitated. For example, you can see the plot here. So 20 megawatt to 50 megawatt is the forbidden zone for this particular hydro unit. So what AGC does is when frequency is more than 50 hertz, the AGC quickly brings the set point down towards its minimum level, and uh, to cross the forbidden zone, there is a wait time of around 5 minutes, which we amicably agreed with the hydropower plants. Like because there's a if we continuously move the unit to in the forbidden zone always, there will be a sense of irritation for the power plant operator. So that's why there is wait time of 5 minutes, and again when the conditions are conducive, then we move the set point back to its schedule value. And when the frequency is low, we try to increase the set point. Although frequency actually has decreased from this point around 16.8 hours, still we had to wait for 5 minutes and then only we could increase the set point here. So those kind of customizations are also done for the hydropower plants which have Francis turbines. So, like I told, the hydropower plants have Francis turbines. So, those the limits are also recorded in our AGC software. And there are some customized features like we respect the forbidden zone, and uh, and AGC will respond only to sustained area controller deviations only, because only if the for at least 20 seconds, if the um, area controller is in the direction that it will enter the forbidden zone for at least 50% of the forbidden zone, if it is going to enter, then only the AGC will move the set point. Similarly, there is a wait time of around 300 seconds for the actual generation to cross the forbidden zone. After the actual generation crosses the forbidden zone, sorry, then only set point will be issued again to cross the forbidden zone. This feature will avoid frequent travel through the vibration zone, and there are some other custom threshold also that are used. So there are what are the modes of operation? NLDC operates uh, all these control areas in flat frequency control mode by default for ensuring economy in the grid. Because in flat frequency control mode, we use all the resources based on the requirement in merit order. In case of congestion or anticipated congestion, uh, with flows exceeding the available transfer capability limit, we operate those particular areas in tie line bias mode, where we look at both the tie line component of the ACE and the frequency component of the ACE also. If there are any radial control areas with commercial or technical requirement for strict adherence to tie line schedules, then those areas are operated in flat tie line control mode. And we operate the power, sometimes we suspend the power plants also, like if there are any software updations or reboots at an LAC. In the suspended mode, AGC sends control signal to the power plants, like to make the AGC correction to 0. So power plant also employs several limits and checks. This is a snapshot of an actual power plant. So where delta P is made equal to 0 automatically when AGC suspend status is set to off, or if there is any communication failure, or if the AGC is turned into local by the power plant, local mode of operation by the power plant. So if the circuit breaker status is off, then obviously we have some um, we have some requirements, like they make all the limits 0. If the unit takes the if the plant takes a particular unit into local, we make the cap max, cap min, and ULSP equal, so that we don't see the reserve in those particular units. Similarly, there is a standard operating procedure, and the power plants have to adhere to the standard operating procedure. Okay. So this control room monitor, this was on 15th August 2021 night shift. Just after COVID, we were unsure how the agency will behave, because there were only very few people manning the control room, only 2 people manning the control room after the lockdown restrictions were eased. So you can see agency beautifully managed the grid on that day by this yellow line is the frequency, and green is the AGC regulation megawatt in uh, AGC up and down megawatt. So you can see when the frequency is down, AGC increase the generation of the power plants, and when the frequency is high, AGC decrease the generation of the power plants. So it has managed that redshift very beautifully, automatically, without any manual intervention. So there are several hundreds of parameters that we monitor. We monitor each plant by plant, several parameters of each plant, and there are some consolidated values that we monitor, like reserves, how much are the reserves that are present, how many units are operating under AGC at a particular point of time, um, how is the AGC responding, what is the delta P that the units are adhering to. So all these different kinds of metrics are also monitored in the control room. We also look at the 15-minute up reserves, 15-minute down reserves, what is the area control error, what is the frequency, so on. So next concept that we have to learn is about the smooth days. So AGC programs, they normally use filtering schemes to filter out random variations of ACE, and smooth days is used to control generation. The integral action, there is a PID controller in AGC. So the PID controller corrects the steady state error towards 0. And the area control error, usually we use P and I mainly, so D is not employed. And the area controller deadband is around 10 megawatt, as suggested by the suggested in IEGC. And there are exponential moving average filter to filter out the noise, and there is a PID controller to create smooth days. So we provide ACE after the PID controller and the EMF filter, we get smooth days. So this controller is tuned based on simulation studies and operational feedback. We have published a report also. You can just click on this and read that report. And the AGC uses smooth days, which is the output of the PID controller. Tuning the AGC PID controller is typically done using a combination of simulations and engineering judgment in this industry. So we see the system response, and gradual tuning of various parameters is done for tuning this controller. The model is tuned against different events like generator tripping and load loss events. And you can see the ideal tuning will be something like this. If we have very small integration time, then it can lead to overshoots. If we have large integration time, it can be very sluggish. So, and this is a very good reference on AGC, like Intelligent Automatic Generation Control by Hassan Bevrani. And this also we refer. Um, I think we can skip some of the slides and for time's sake. So we also see there is a time delay of the AGC response. Uh, while the plants adhere to the signals, there is a delay in actual megawatt by the power plant in response to the AGC set point. You can see that the blue line is the AGC set point, and the pink line is the actual megawatt. So obviously there is a lag. The actual megawatt is lagging the AGC set point. So this lag is around 3 minutes. So that is because of the steam parameters have to be stabilized, and if we are too aggressive, then there can be steam parameter oscillations. So always the AGC cycle period versus boiler thermodynamic process period also has to be seen, and we take this feedback from the power plants. So how do we allocate this smooth days to different generators is that there is a thing called as custom participation factor. So the AGC provider will be selected based on regional basis by the nodal agency for providing AGC up and AGC down. For upregulation, the regulation component is calculated based on the normalized value, directly proportional to ramp rate and inversely proportional to variable cost. That means, suppose if you have to give upregulation, we will start from the cheapest plant to the costliest plant. 50% weightage is given to the variable cost, 50% weightage is given to the ramp rate. So, like we discussed, economy always has to be maintained. Even in ancillary service, also economy has to be maintained. Economy means always we start with the cheapest resource first while increasing. Similarly, for down regulation, the down regulation is calculated based on the normalized value, directly proportional to ramp rate and directly proportional to variable cost. While issuing down regulation, we start with the costliest power plant. So, like that, we try to bring in economy here also. After SCED, the input output of the SCED is used as basis for the AGC, and within AGC also we use the variable cost for setting the merit order. Okay. So how is the accounting and settlement done in the AGC? So there is a regional deviation and ancillary pool account. So that is fed by the overdrawing and underinjecting entities. And the underdrawing and overinjecting entities, they usually get paid from the pool. So for all the AGC app providers, they receive two types of compensations. One is the energy charge or the compensation charge for the energy that they have contributed under AGC for all the AGC app providers. And for all AGC app providers, there is a incentive also, performance-based incentive of 50 paise per kilowatt hour, up to 50 paise per kilowatt hour uh, for every 5-minute AGC megawatt up and down. Similarly, the AGC down providers, they refund their energy charges to the pool because they have decreased the generation. So they have not spent the fuel, right? The coal is still remaining with them. So they refund back the energy or compensation charges which they have received from their beneficiaries back to the regional pool. But they receive, the agency down providers also receive incentive of up to 50 paisa per kilowatt hour from the pool. So the agency up providers are paid and agency down providers have to pay back to the pool. And there is a incentive uh, based on the 5-minute megawatt hour uh, uh, for both up and down regulation. Why we and while doing this accounting and settlement for AGC, we use scatter data. Why scatter data is used? Because the if you put an energy meter at the terminals of the power plant, that energy meter cannot distinguish between what is the increase because of AGC or what is the increase because of schedule. So that's why we took the regulatory consent and we use scatter data for accounting, AGC accounting. And why do we use 5-minute megawatt hour for incentive calculation is that we have seen in the earlier slide, like every 5 minutes, the system frequency will go either above 50 hertz or below 50 hertz. If you look at a 15-minute time period, it might so happen that the 15-minute average megawatt hour will become zero. So that's why we use 5-minute megawatt hour so that the services provided by these power plants are properly respected. So we have a data verification process also. We have an in-house accounting software where we take data from the power plants. We verify it using the ASCEND data and telemetered feedback data, and we send this reconciled data every week to the regional power committees for accounting and settlement. The performance of the plant is is measured and monitored daily. So how is the performance evaluated? So for example, the National Dispatch Center gives a 50 megawatt up instruction. The power plant also has to generate 50 megawatt up. Then Y is equal to X in the scatter plot. Uh, if the power plant only generates Y is equal to 0.94x, if it generates only 40 megawatt when we gave 50 megawatt instruction, then the Y is equal to 0.8x. So we call it as 80% performance. Like that, every 5 minutes, we evaluate this performance and we trend fit this scatter plot to a Y is equal to mx chart. And for each plant, every day, a performance metric is evaluated. So the input, um, the x-axis is the input which is the uh, delta P that is sent to the digital control system of the power plant under AGC. And the output is the actual megawatt minus the unit load set point minus the governor megawatt, so that the output delta P is under AGC is measured. So the output versus input is measured and monitored daily. So there is a performance-based incentive that is given by CRC, like a power plant with 75% to 95% performance, it will get 40 paisa per kilowatt hour. Above 95%, it will get 50 paisa. Below, there are slabs like 30 paisa, 20 paisa per kilowatt hour. So for example, here you can see the blue line is the actual megawatt and red line is the AG set point. So the actual megawatt is following the AG set point very closely. So for this plant A showed 80% performance. Similarly, plant B also is very closely following the AGC set point in actual, and it has exhibited 94% performance. So both plants A and B receive 40 paisa per kilowatt hour here, because all these conventional power plants, they have some inherent delay that is acknowledged. So most of the conventional power plants, they fall in between this 75% to 95% band. So the IBRs, batteries, solar, wind, they are expected to join this greater than 95% performance bracket. We also have conducted a AGC pilot project at Devikot Solar. So with high RE penetration, frequency control during high solar periods, it's a challenge. So flexibility attributes are needed from the thermal power plants. We try to bring the thermal power plants to their minimum turn-on levels during high solar hours, so as to allow more solar integration into the grid. But sometimes a down regulation to solar power plants also may be needed, because for frequency control. So this will become an efficient RE management mechanism based on grid conditions. So this is the pilot. Like I told, the red line is the AGC set point and the blue line is the actual megawatt. So you can see that the AGC actual megawatt is very closely following the AGC set point during the high frequency period. During low frequency period, the actual megawatt saturated the MPPT value corresponding to the prevailing irradiance, and this is set at around 200 megawatt. So like this, solar also can be controlled through AGC. Okay. So what are the challenges? There is an increasing, we are trying to increase the pool of the AGC generators from the present central sector power plants to state sector power plants also. There is a choice for the state sector power plants to join the well-established SRS mechanism. We have been operating AGC from July 2021, 24/7 Pan India. From 2017, we have been operating AGC as a pilot project. So it is high time we increase the pool of these AGC generators so for better frequency control, because with this high RE penetration, it will be very difficult to do any manual frequency control any longer. So there are ongoing initiatives for AGC of solar and battery storage in India. We are also experimenting with the new technologies like demand response and hydrogen electrolyzers. And low ramp rate declared by the coal-based power plants it is a challenge. And thermal power plants, they prefer to operate around their base point. They offer only plus or minus 5% around their base schedule, because of the constraints on boiler combustion side. Managing so automatic mill cut in cut out, there also the power plants can do some more innovation, and they can come up with more flexible operation there. And managing forbidden zones and daily hydro constraints is a challenge. And we are trying to uh, increase the liquidity in market-based ancillary service also. So we produce a lot of literature over a period of years on this automatic generation control aspect. So I recommend you to. I've provided links also here. If you click the link, you can get all this IEEE, SIGRE, and other some reports in the public domain in our NLDC website. You can just read them. Thank you. Any questions? Or to Sanjeev sir and Das sir. Yeah.
Yes, sir. Thank you very much, sir. Really, it was a very wonderful presentation regarding the AGC status in India. So, if what I want to ask, there are a lot of people or a lot of students who are working on AGC problem in our institute. So, on what should be the focus areas for those students so that they can provide value to this broad area? So that input we want, mostly because they are following literature, but some practical inputs from your side will be highly valuable.
Right. So one thing, actually, AGC is a very well-researched topic already, right? So on this, what further can be done is all these new entries into the AGC domain, like batteries, um, or the IBRs. Different IBRs are coming, like wind, solar. They're already there, and the hydrogen electrolyzers and the demand response or the smart grids that are coming. How they can be seamlessly incorporated into AGC, that can be seen. And for example, you see the AGC operation with conventional power plant is slightly different than AGC operation with this IBR. Suppose if you ask a conventional power plant to suddenly go to zero, it will not go because there is a ramp rate limitation inherently within the steam turbine and the hydro turbine. But the IBRs, if you ask them to go to zero, they'll go to suddenly zero, which may or may not be needed by the grid. So the coordination and an economical operation of all these integrated resources, that can be well thought upon. And there are several technical limitations with respect to IBRs also. We expect the batteries to be very flexible. Batteries also have some sometimes they can also exhibit inflexibility. The inverters may have some challenges. So these all have to be brought out clearly with respect to AGC also, and the battery management systems, how they can be tailored for AGC operation, how to manage the state of charge, what are the algorithms that can be used to manage the state of charge of these batteries. So they also can be further streamlined. For thermal power plants, the mill cut in and cut out, it is semi-automated or manual at many places in India. So that how we can go for a fully automated mill cut in and cut out mechanism. What are the latest state of art? Are there any further you know adaptive techniques to for this mill cut in and cut out? So those also can be thought upon. So these are some challenges that are readily coming to my mind. Yeah.
Then I have also seen
literature.
regarding hydro units, I have seen forbidden zones, I think is also an interesting
Yes. The forbidden zones, how to traverse through those forbidden zones in
this is also important.
coordinated manner, so that we extract the maximum flexibility out of these hydro plants. And uh, what will be the ideal timing in between crossing two forbidden zones. So those things also can be thought through. Yeah.
Yeah, sure, sir, sure. Thank you, thank you. If any participant has any other question, they may write in the chat box and I can explain it to our.
Yeah, there is one in the chat box by Subham.
Okay. So what are the
What
emerging research challenges and potential control strategies for enhancing AGC performance under high RE penetration, considering the coordinated participation of EVs and energy storage systems? This is a uh, you know uh, this is a very evolving topic and a very relevant topic. So the EVs, obviously they will not be participating directly under AGC, right? So maybe the how we can coordinate with an aggregator for getting that demand response from the EV aggregators? That can be definitely a good research question. If there are enough EV hubs in India, how they can, just like we are wiring the power plants, what should be the process for integrating all these EV hubs also into our AGC software? So that can be uh, one research area.
Thank
So
you,
there
sir.
are coming to challenges. It's just um, but it is we have to dwell more on what these resources can do, and where is the limit. So mainly, what is the maximum megawatt that they can offer? That has to be clearly be delimited to the system operator every 4 seconds. So how to get that from these aggregated resources? Similarly, what is the minimum value that they can provide? So minimum, maximum, and what is the ramp rate at which they can provide this service? Obviously, all these IBRs are very quick, so they're expected to respond at very high ramp rate. But and when they will be available, uh, and when should we call them? So what is the merit order in which we should call these resources for AGC regulation? So these kind of aspects can be thought through. How to map it to a conventional resource, so that they can be integrated into our software. What are the changes that might be needed in the AGC software? So those kind of aspects from the EMS side also you can explore.
Thank you, sir. Thank you. I also request Phanisankar sir to please share this presentation with us as an email so that we can upload it to AICTE website for the reference of our participants. And
Definitely.
if there is no questions, so we can wind up. On behalf of organizing committee of this FDP, I thank Mr. Phanisankar to spare his valuable time and giving us valuable inputs. Thank you. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.